Thermo-chemical processes, an overview, Part.1. Lecture by Dr.G.Subramanian, Chief Scientist Retired, CSIR, Central Electrochemical Research Institute. The thermochemical processes transform biomass into usable energy within less time as compared to biochemical methods that proceed up to many hours for transformation. Thermochemical methods are employed for either significantly reducing the sludge solids content or pre-treating sludge upstream of anaerobic digestion, shortly called AD, to increase the biodegradability of the organic carbon. When operated at elevated temperatures, that is for solids destruction rather than for anaerobic digestion, pre-treatment, they provide energy recoverable either as heat for oxidative processes or as combustible gas or liquid non-oxidative processes. Thermochemical methods are used for either significantly reducing the sludge solids content or pre-treating sludge upstream of anaerobic digestion to increase the biodegradability of the organic carbon. As with stabilization and drying processes, thermochemical processes produce a stable sludge product. When operated at elevated temperatures, that is for solids destruction rather than anaerobic digestion pre-treatment, they provide energy recoverable either as heat or a combustible gas or liquid. There are two chemical states by which the solids content of sludge can be reduced thermochemically. One is by oxidative, another is by non-oxidative method. As such, the thermochemical process types are analogous to biochemical digestion methods for solids destruction, which takes place in the presence that is aerobic digestion, or absence of air, that is anaerobic digestion. Sludge thermochemical treatment. First one is oxidative process. Under this we have three categories: incineration, wet oxidation, and supercritical water oxidation, shortly called as SWCO. Then another one is non-oxidative processes. Among this, first one is gasification, that is partial oxidation. Then hydrothermal processes. Under this we can broadly classify into three. First one is hydrothermal carbonization. Next one is hydrothermal liquefaction. And the final one is hydrothermal gasification. As it proceeds from hydrothermal carbonization to hydrothermal gasification, the temperature increases. The temperature of the processes increases. The next one is pyrolysis. Oxidative thermochemical treatment of sludge. Oxidative methods for sludge thermochemical treatment comprise incineration, wet air oxidation, shortly called WAO, and supercritical water oxidation, shortly called SCWO. These processes convert the combustible organic matter to primarily carbon dioxide and water, along with other gaseous oxidized byproducts such as nitrogen oxides or NOx present at lower concentrations and a solid residue. The methods differ in terms of operational temperature and pressure, the required feed sludge water content, and the nature and concentrations of gaseous and solid products generated. Incineration of sludge. Incineration or combustion of sewage sludge is the most widely accepted alternative end disposal method after land spreading. It is an oxidative method converting the organic carbon, nitrogen, sulfur, and phosphorus into gaseous and predominantly mineral, that is inorganic solid products. Example of sewage sludge incineration process, you can observe a video. the coming slide. Incineration is the most established and widely implemented of the sludge thermochemical treatment processes, with the original sewage sludge incinerators installed in the mid of 1930s. There are currently hundreds of large sewage sludge incinerators in operation across the world, most of which generate power as well as converting the sludge to ash. The incineration process is effective in eliminating the feed organics, produces little odor, provided the flue gas treatment is effective, and generates a solid ash product which is stable and substantially reusable. The heat generated can be recovered from the flue gas stream and reused directly and or converted to electrical power. Incineration becomes autothermal, that is sustained by the heat generated by combustion process at sludge moisture contents below 33%. However, the generation of secondary pollutants such as dioxin, furans, nitrogen oxides, sulfur dioxide, as well as dust particles demands ancillary processes for removing these contaminants from the flue gas, adding to the overall cost. In addition, although most incinerators are energy positive, the overall energy balance of the process is affected by need to thermally dry the sludge prior to incineration. Sludge incineration reactors are predominantly configured as fluidized beds. This configuration has largely displaced the multiple hearth furnaces originally implemented. Fluidized beds operate at a temperature of 800 to 900 degrees centigrade and under atmospheric pressure. Particle retention times are in the order of 2 seconds within the reactor itself at the upflow air velocities of 0.5 to 1 meter per second used. You can see the video link given below. As it has copyright issue, we cannot attach the video here. You can go through this video using this link given below. This illustrates the Autotech sustainable sewage sludge incineration for the canton of Zurich. The following 9 slides images throw more light on the video. This is the largest and most advanced incineration plant in Switzerland, completed in 2015 with an annual capacity of 1,100 tons. Complies strictest environmental standards set by European Union compliances. Benefits of Autotech's solution are self-sustaining thermal treatment, minimal environmental emissions, residue ash can be used for phosphorus recovery. This is the view of sludge bunker of the incineration plant. The volume capacity of 2,500 meter cubed. So this is the view of thermal sludge dryer of the incineration plant with an inlet dry substance content about 22 to 30% and outlet dry substance content about 35 to 45%. So this is the Autotech fluidized bed incinerator, fully refractory lined, combustion temperature between 870 and 950 degrees centigrade with SNCR, that is selective non-catalytic reduction, is a post-combustion emissions control technology for reducing oxides of nitrogen by injecting an ammonia type reactant into the furnace at a properly determined location. So this is the heat recovery boiler of the Autotech's incinerator plant with the capacity of 9 tons per hour of steam at 450 degrees centigrade and 60 bar pressure. So this is the view of the steam turbine, the capacity of electrical power output 900 kilowatt. So this is the view of the electrostatic precipitator of the incineration plant with greater than 99% ash separated for further use. So this slide shows you the emissions level from the plant. Dust less than 10 mg per meter cube. Lead and zinc less than 1 mg per meter cube. Mercury less than 0.1 mg per meter cube. Cadmium less than 0.1 mg per meter cube. Sulfur dioxide less than 50 mg per meter cube. Oxides of nitrogen less than 80 mg per meter cube. Hydrogen chloride less than 10 mg per meter cube. Hydrogen fluoride less than 1 mg per meter cube. Ammonia less than 5 mg per meter cube. Carbon monoxide less than 50 mg per meter cube. PCDD and PCDF less than 0.1 nanogram per toxin equivalents per meter cube. What is PCDD? Polychlorinated dibenzodioxins. And PCDF, polychlorinated dibenzofurans. Complex chemicals containing chlorine. Wet air oxidation of sludge. Wet air oxidation of sludge, or more commonly wet air oxidation, shortly called WAO, if carried out in air rather than pure oxygen, is a thermal degradation, hydrolysis and oxidation of organic matter at high temperatures and pressures. Unlike incineration, the most established oxidative thermal method, the wet air oxidation process, does not generate secondary pollutants such as dioxin, furans, oxides of nitrogen, sulfur dioxide. Instead, the process can be operated either to enhance the biodegradability of the sewage sludge or to substantially mineralize the organic matter, that is, convert it to bicarbonate and carbon dioxide. Wet air oxidation is an established process, having been originally commercialized in 1960s. Hundreds of wet air oxygen plants have been installed globally for the treatment of challenging industrial effluents containing biorefractory organics and are toxic compounds which cannot be treated by classical biological processes. An example is the Zimpro process from Siemens. There exist a few examples of full-scale wet air oxidation plants used for sewage sludge specifically, which employ the TOP process technology from the company 3V Green Eagle. The schematic presentation of wet air oxidation WAO process, Zimpro process. You can see the sludge holding tank, then gas liquid separator, then you have heat exchanger and a reactor. Air is supplied to the heat exchanger. So from the heat exchanger you can see gas and liquid are pumped out, and from this you can see effluent, liquid effluent and solid liquid. In the solid liquid separated at the left edge you can see both liquid effluent and ash are separated. So thus by effluent treatment has been successfully done. Wet air oxygen operates in an aqueous environment and therefore does not demand drying of the sludge. Sludge destruction by wet air oxygen typically employs temperatures between 260 and 320 degrees centigrade at pressures of 20 to 150 bars and resident times of 0.25 to 2 hours. Under these aggressively oxidative conditions, a chemical oxygen demand, that is COD removal of 70 to 85% is obtained, with removal increasing with operating temperature and retention time. The high temperatures at which wet air oxidation operates demand correspondingly high pressures to ensure that the water remains in the liquid phase rather than gas phase as would arise at reduced pressures, and the salts therefore remain dissolved. Salts precipitation has been identified as being the possible cause of corrosion in early commercialized wet air oxidation technologies. Pressurization also increases the dissolved oxygen concentration, adding to the oxidative potential of the process, but also to the corrosion propensity. Wet air oxidation application upstream of anaerobic digestion is intended to enhance the biodegradability of the organic matter in the downstream of anaerobic digestion reactor. For this duty, lower temperatures 100 to 200 degrees centigrade and pressures less than 20 bar are used, sometimes with the addition of catalyst. The wet air oxidation performance is measured in terms of the increase in either the liquid phase organic carbon or the subsequent removal of volatile suspended solids, shortly called VSS, by the anaerobic digestion process. Most recently, there has been interest in the potentially high value intermediate oxidation products, that is, low molecular weight organic compounds such as acetic and propionic acid, generated by wet air oxidation. While these carboxylic acids are produced in appreciable concentrations by wet air oxidation process, extracting and purifying them for reuse remains a challenge. Supercritical water oxidation of sludge, that is SCWO. Supercritical water oxidation refers to the oxidation of organics in water in the so-called supercritical phase of water. These conditions represent the most aggressive in terms of temperature and pressure of all thermo-chemical oxidation processes. Supercritical refers to the state of water within a specific region of pressure greater than 218 bar and temperature greater than 374 degrees centigrade. The physical properties of water, specifically its density, viscosity, diffusivity, dielectric constant, and its subsequent solubilization of organic and inorganic compounds, change significantly in the supercritical region. As such, supercritical water is effective both as a reactant and a solvent. Supercritical conditions can be used for both oxidation, supercritical water oxidation, and gasification, supercritical water gasification. In the oxidation mode, as with all oxidation reactions, degradation of the organic matter is enhanced by using an oxygen-enriched gas source, as well as elevated temperatures and pressures. The process becomes autothermal, that is, sustained by the oxidation process without the requirement for further heating, at around 10% sludge solids concentration or 50 grams per liter of chemical oxygen demand for typical municipal wastewater sludge. Supercritical water oxidation was originally commercialized in the 1980s but was subject to a number of operational challenges. 1. Corrosion under the acidic conditions created, salt precipitation or accumulation from desolubilized inorganic matter, and erosion from solid particles. 2. These challenges and corrosion in particular led to the decline in implementation of the technology. Most of the supercritical water oxidation plants installed in the 1990s and early 2000s, primarily for treating challenging industrial effluents, have been shut down. Of the few commercial supercritical water oxidation technologies which currently exist, the superwater and aquacritox process technologies have both been successfully demonstrated against a municipal wastewater sludge feed. Both employ a pure oxygen gas source and a tubular reactor configuration. The sludge is pressurized to approximately 260 bar pressure, then heated to 250 to 300 degrees centigrade. The subsequent oxidation reaction, which takes place in an array of steel tubes, may then raise the temperature up to 600 degrees centigrade, sufficient to mineralize the organic carbon within 1 minute. Organic nitrogen and sulfur are converted to nitrogen gas and sulfate respectively. the reactor temperature is apparently low enough to avoid oxides of nitrogen formation. So this picture graph represents the states of water as a function of temperature and pressure. You can see triple point, critical point, supercritical fluid. In thermodynamics, the triple point of a substance is the temperature and pressure at which the three phases gas, liquid, solid of that substance coexist in thermodynamic equilibrium. It is the temperature and pressure at which the sublimation, fusion and vaporization curves meet. If we move further above, you can see critical point. There is a special mix of temperature and pressure. We call it critical point, where the difference between the liquid and gas ceases to exist. For water, this happens at 374 degrees centigrade and 218 atmospheric pressure. Normal air pressure is 1 atmosphere at sea level. And you can see a supercritical fluid, shortly called SCF, is any substance at a temperature and pressure above its critical point, where the distinct liquid and gas phases do not exist, but below the pressure required to compress it into solid. It can effuse through porous solids like a gas, overcoming the mass transfer limitations that slow liquid transport through such materials. So, supercritical fluid are superior to gases in their ability to dissolve materials like liquids or solids. Also, near the critical point, small changes in pressure or temperature result in large changes in density, allowing many properties of a supercritical fluid to be fine-tuned. This is a pictorial depiction, illustration of supercritical water oxidation process for sewage sludge treatment using aquacritox technology. You can see you have high pressure pump which pumps in sludge through heat exchanger and through tubular array reactors it goes through, and oxygen has been supplied. And owing to the reaction, it passes through cooler and pressure reduction happens, and finally you can off gas, a combination of carbon dioxide, oxygen, nitrogen comes out, and the liquid effluent comes out at the bottom. Thus the process eliminates, it treats effectively the sewage sludge, separating both gas and liquid effluent. Thank you very much for watching this video, and thanks for your patience.